Okay, so I'm super happy to be here today to tell you about the story of our company. I'm going to start off with a flashy announcement that we had in December of last year when we got a $60 million grant from the Graph Foundation. And for the rest of this class, I'll explain to you what it means to get a $60 million grant and how we did it. And I'm going to try to emphasize some of the aspects of what we're doing that I think are going to be enduring features or enduring needs of the space. Yeah. So this is a timeline of our company, and we have 3 threads in the evolution of our company. And below the evolution, or below the timeline, I also have the price of Ethereum. And the reason that I have that there is to emphasize my opinion that I think a lot of what has happened for our company comes down to being in the right place at the right time and having the right preparation. And also, I think networking is super important. So this kind of gives you an idea of why things were happening to us when they were. So we were founded in February of 2020, and our initial focus was on fully homomorphic encryption. We had 4 co-founders. Ahmet Ozkan, he is our CEO. Ahmet, would you mind raising your hand? So Ahmet has a PhD in physics. He spent the first part of his career doing silicon research for IBM, and then he transitioned into machine learning. And he went to IBM Research, and he led the machine intelligence department. Aaron introduced me, and then Dr. Gökay Seldamli, he is a cryptographer. He's right there. Gökay and I are academic brothers. We have the same PhD advisor. Our advisor started the largest cryptographic engineering conference. It's called CHES. And Gökay has spent his whole career focused on cryptography and cryptographic engineering. Gökay was previously at San Jose State University, and prior to that, he was at Samsung. And at Samsung, he designed all of the cryptographic hardware accelerators for Samsung's SIM cards. So Gökay has millions of cryptographic hardware accelerators deployed. And then our 4th co-founder is Alexei Yasemin. Alexei's sitting over there. Alexei is our lead developer. He has a background in device physics, and he also made a transition into machine learning, and he worked with Ahmet at IBM Research, where he was the lead architect on a system that had around over 1,000 FPGAs, and they built this machine to do evolutionary algorithms. So you can see that our team has a mix of AI and cryptography, and that's been the theme of our story from the beginning and to now. Our initial focus was on encrypted computing. Specifically, we focused on fully homomorphic encryption, which allows you to do computations directly on encrypted data. And our beachhead market was machine learning as a service. So we were going to do ML, specifically we're going to do ML inference on the cloud. And our competitive advantage was algorithmic and hardware acceleration. So I have a question at this point. Is anybody in here a cryptographer or focused on cryptography in your studies? Nobody? Okay, so then what you may not know is that, okay, so something interesting is that FHE was actually created or made practical by a PhD student here at Stanford fairly recently, I think around 2014, 2013. It was done by Craig Gentry, who is a PhD student of Dan Boneh. And Professor Boneh is a professor here, and he'll be speaking next week. So not only is he an awesome presenter and teacher, but he also has made tons of contributions in the field of cryptography. Everything I'm going to be talking about today, he has influenced. So here's a use case to help you understand the use of FHE, fully homomorphic encryption. And we built this use case out for demos. So imagine you have a smartwatch and it can record your heartbeat data. You can encrypt that heartbeat data locally on your watch. You can then send that encrypted data to the cloud, And on the cloud, even if people wanted to hack or see the data, they can't see the data. But using FHE on the cloud, we're able to run a deep neural network to predict whether the heartbeat is normal or abnormal. And then you send the encrypted, everything's encrypted. You send the encrypted result back to the user where they decrypt it. And we were able to get this whole thing running in about 1.3 seconds. And that's versus the off-the-shelf tools, which would take about a minute. So we were able to do this fully homomorphic encryption in real time. And if you've heard, has anybody heard of FHE before this class? Okay, quite a few people. Yeah, so anytime you hear about FHE, you hear that it's not practical. It's interesting, but it's not practical. It is practical for some applications. In addition to these use cases that we proved out, we were also working on algorithmic accelerations. This comes from Gokai's previous research during his PhD. We designed a new NTT algorithm. NTT is a Fourier transform for integers. And we were able to run our NTT. So NTT is needed for fully homomorphic encryption. You need to use it over and over again when you're multiplying two encrypted numbers. And so you want to make it as fast as possible. And if you look at the table, you can see our results on the right-hand column. That's the latency to multiply two numbers in microseconds. And we were able to get a lot faster speeds than other people in industry, including multiple results from Microsoft. This work on FHE was allowed us to get seed funding from the NSF. So NSF has funding called SBIR. It's for small businesses, and it's non-dilutive funding. It doesn't have a lot of overhead. It's usually a small amount of money, but it's really useful when you're a small company. We were also so our FHE work also allowed Amit and I to get fellowships from Activate. Activate is a deep tech startup that's run out of Berkeley Lab, and they give you 2 years of salary, and they give you travel money. And if this is a really good program, especially if you're doing a deep tech or hard tech company, I highly recommend checking out the Activate Fellowship. They also don't take any equity, and they don't have any requirements from you. So we did FHE for about a year. We were funded, personally funded. We were self-funded. We didn't have any VC money, and throughout that year we developed our tech, but we weren't able to get any market traction. We were targeting beachhead markets of either fintech or healthcare. Neither of those domains care about cutting-edge cryptography. Why? Because those domains make decisions based on regulations, and FHE isn't regulated, so it doesn't help them at all. Luckily, around that time, you can see that crypto was taking off, and we were introduced to the graph protocol. And the graph, it turned out they had needs that were 100% overlap with our skill set. So we applied for a Wave 1 grant with the graph, and we started working with them initially in automation and optimization. I'm going to introduce the graph in a moment, but I'm going to motivate it by digging down into the weeds a bit with Ethereum. So Ethereum, does everybody in the class know that Ethereum is actually a distributed computer, and that all of the validators on our Ethereum are all running the same program? Anytime a transaction is submitted, every validator in Ethereum has to run this program. So it's very expensive to run transactions on Ethereum. So etherscan.com is like a debugger for Ethereum. And you can go there, if you ever make an Ethereum transaction, you can go here and you can look it up, and you can see exactly what happened. And if you dig down under the hood, this is what all your transactions look like. They're just they're just binary blobs. Ethereum gets about 1 million of these things per day. And the role of Ethereum is only to provide security. This distributed computer, their only job is to say, okay, I have a new transaction in. Let me update the state of the computer. Is it valid? Yes, that's great. If not, it rejects the transaction. The role of Ethereum is not to tell you what the state of the machine was a year ago or 5 years ago. It's not tracking. It's not tracking that. It's like a computer on your desk. The job of your computer on your desk isn't to tell you its state a year ago. It's to tell you the state now. Applications can tell you the state of certain aspects of your computer a year ago. And that's what the graph does. Its job is to tell us the state of the system in the past, or if we want to do more processing, post-processing of the transactions that are done on Ethereum, the graph can do that for us. So the graph's mission is to index all blockchains. The protocol itself runs on Ethereum currently, but the workers in the protocol are watching all of blockchains. And the graph, as many of you know, it provides an open API, and this is basically makes it so anybody who's building applications can have an easier time of getting data that they want for websites or some other higher level applications. It's also permissionless, which means that anybody can use the graph without applying. You don't have to sign EULAs. You know, like if you've ever written an Apple app, you have to go through all sorts of hoops to get access to their SDK. You don't have to do that with the graph. You can just start using it. It's also geo-distributed and censorship resistant, and it's used by all of the major applications in Ethereum and across many other blockchains. So here's an example of it being used. Uniswap is a decentralized exchange, and it is the largest application in crypto, in blockchain, outside of Bitcoin. So Ethereum and all other Ethereum-like chains, Uniswap is the biggest. If you go to info.uniswap.org, you can see information about this exchange. And if you were to click on the developer settings for this web page, you can see that all of the data that it's displaying. So this data is like total value locked into these smart contracts, how much volume is sent through these exchange. All of this data is coming from the graph. So the graph is where when you're looking at crypto applications, you're typically getting data from the graph. The graph is also a decentralized protocol. This means that it's all run by individuals and small businesses. There's no centralized organization that controls this protocol. There are 6 different roles in the graph protocol, and the 2 most important ones are consumers and indexers. Consumers are the people who want to query data for their applications, and indexers sell the data, or they provide the data. So now I'm going to transition into what Semiotic is doing in the graph. We specialize in 2 things still. We're still doing AI type work and cryptography work. On the AI type work, we specialize in simulation and optimization. So the graph, because it's decentralized, it has to incentivize people to run and operate the graph. So there are all these complex incentive mechanisms to get people to do the roles that we need done so that the protocol operates. And the awesome thing about crypto is that most of the projects are open source. And so here we have the graph. All the code is open source. It's actually a really large economy. And you can containerize this thing, and you can simulate the entire economy. And once you can simulate this thing, you can then start asking what-if questions with your simulations. And then you can use these simulations to guide changes to the mechanisms of the protocol. So in addition, once you have the ability to simulate, you can start doing more interesting things like training reinforcement learning agents. And I'm going to walk through a case study where we trained pricing or agents to compete over pricing in the protocol. Okay, so in the graph, we basically have, if you want to boil down what the graph is, it's a query market. People have data for sale, and people want to buy data. And the people who are selling data are called indexers, and there are many indexers. Currently, there are about 200 indexers. And all of these indexers are competing to be able to provide the best service. And they compete, how do you define best service? Well, it could be latency, it could be uptime, it could be the data freshness, and it could be price. And price plays a big part in the competition. And then on the other side of the query market, you have consumers. And then, of course, they want to spend as little as possible for their data. So we wanted to provide automated agents for the indexers so that they can learn how to adjust their prices so they're making as much revenue as possible. And we have currently done that. We used reinforcement learning and deployed some online agents And we have agents that are currently in beta. And what you see here on the x-axis is time. And on the y-axis, we have revenue. And so you can see that this agent, what this agent is doing is it's learning to adjust its query prices over time such that its revenue is increasing. On this topic, we're going to be presenting at DevCon. Who is going to DevCon in the room? I see one, two, just one? Okay, a couple people are going to DevCon. So this is Ethereum's main conference. And if you want to come up to speed with what's going on in crypto, and if you want to really accelerate your learning and your networking, DevCon is an awesome conference to go to. It's going to be in Bogota next week. Before I leave this slide, I also want to point out that within the Graph protocol, we have an economics working group, and we have PhDs in operations research, optimization, robotics, AI, and we're all working on many problems beyond just this. So the protocol is very complex. There are many interesting problems, and if you're in economics or if you're in optimization or any of these other fields, then this is a great area. We believe this is a great area to do work and also get publication worthy results out of. So now I'm going to transition into our cryptography efforts. And I'm going to I'll be focused on verifiable computing and verifiable data. Specifically, I'm going to be talking about verifiable payments. So the context in the graph is that anytime someone is buying queries, asking for queries, they have to sign a receipt saying that they're willing to pay for those queries. And then it's the job of indexers to collect all of those receipts and then submit them for on-chain so that they can get paid. So our goal with verifiable payments was to prove that all of the signatures were okay and sum the amounts. So why can we not simply have data buyers, submit an on-chain transaction and have the data sellers submit their data on-chain in response? There are a couple reasons. Can anybody tell me?
Efficiency of the blockchain, there would be too much data on it.
That's right. It'd be too much data. It would be incredibly expensive. All parties would go bankrupt that day. So what we would prefer is to do all of our computations off-chain. And we want to interact. You always want to interact on-chain as little as possible for cost reasons. So this is exactly what verifiable computing lets us do. Verifiable computing is kind of the superset, and then I'm sure many of you have heard about snarks or ZK snarks. These are provable ways to do computations off-chain. And what happens is you have a worker, who we call a prover, do the original work that we want done, and while they're doing the work, they create a proof. They then submit the result and the proof to the Ethereum virtual machine. They submit it on-chain, and then on-chain, the work or the proof can be checked cheaper than it would have been for the on-chain, for the EVM to do all of the computations to begin with. So it's cheaper to check the proof than it was to do the work to begin with. And this allows us to push more, this field of verifiable computing, ZK, snarks, allows us to push computations off-chain. So this is another area that's going to continue to, it's really hot right now. And it's going to be, actually here at Stanford, you have an advantage of being here because there's a lot of techniques coming out of Stanford related to the field of verifiable computing. Again, Professor Bonet is leading in this area as well. Okay, so in summary for this section, we're currently developing a snark, which enables high throughput payments for the graph. And this is going to allow indexers to aggregate millions of receipts in an efficient way. Okay. So now this brings me to the to the core developer grant. I'm going to give you a few more details about that. So the grant was non-dilutive. It lasts for 8 years. So you can think of this as like a temporary acqui-hire. It allowed us to grow to 10 people this year. And then next year it's going to fund us to grow to 15. Everything that we're doing is open source, which is great for the employees because they can have artifacts of their efforts. And the company, Semiotic, is also free to expand into other business units, which we have. So this may be the first time that you've heard of a structure like this or something being built like this. So I'm going to spend a few minutes just explaining the organization of what's going on here. Okay, so all of the work in the Graph protocol is managed by what's called the Graph Foundation. So we have the Graph Foundation at the top, and then below that we have 7 different core dev teams. And each of the core dev teams have similar grants to Semiotic. And we all coordinate with each other. Everybody has their own specialty. Edge and Node, they created the protocol to begin with. Streaming Fast, they have technology to index very quickly. Figment has a lot of DevOps expertise. They're really big in the staking community. Masari is well known for their data processing abilities. The Guild specializes in GraphQL, which is not related to the graph. GraphQL is like a database query type language. GraphOps, they specialize in the graph-related technologies and infrastructure. So we all bring our different skills, and we work together to build the graph. So now I'm coming to the last thread and the most recent thread of the company. Like I said, we are free to create new business units, and decentralized finance is the first thing that we focused on. So I'm going to focus, actually our work is focused on a particular aspect of DeFi, and that's related to DEXs, or decentralized exchanges. So a decentralized exchange is a smart contract, and what happens is that we have liquidity providers who deposit tokens into the smart contract. The smart contract is just another name for a program. So liquidity providers deposit liquidity. This would be, in Ethereum, this would be ERC20 tokens into the contract, and they get fees in exchange for people doing swaps with the program. So traders can now, once there's liquidity available, traders can come to this program and they can deposit assets plus their fees into the program, and they can get assets out. So here I'm showing asset A is deposited and asset B is removed. Okay, so a question that you might have is, how do we know that the exchange rate between asset A and asset B is correct? Especially when, in any market, whenever someone makes a trade, they're going to have price impact. So initially, let's assume that asset A and B are balanced. They actually have a correct ratio. And that as more of asset A is deposited, it becomes more and more available. Asset B becomes more and more scarce, so its price is going to go up. Well, it's the job of arbitrageurs to watch these DEXs and look for value arbitrage. And once they see arbitrage, once they see, oh, A and B are out of whack, if I were to deposit asset B, I would be able to get more of asset A back than I can get in any other market. Then arbitrageurs will come in and they will rebalance the pools. Does anybody know, okay, so these arbitrageurs are looking at all the other DEXs. So why not have the DEX watch what the other DEXs are doing? Why not have this DEX watch all of the competitors and all the other DEXs to figure out what the fair price should be? It's because that would require extra logic. it would require many external contract calls to all the other DEX contracts. And every call you do adds extra cost. And that's going to drive up the price for what it would cost to do a trade. And it would actually become super expensive. So that's why it's really clever that Uniswap, so it's actually Vitalik who came up with this idea as far as I understand. Uniswap, Hayden Adams instantiated it. They were the first ones to build one of these things. It's very clever that they're having the arbitrageurs do the work instead of having the smart contract do the work and having to pay for those extra instructions. Okay, so in July of last year, we participated in an ETH Global Hackathon, and we were just curious about the amount of arbitrage opportunities across different chains. So our project is looking at all Uniswap V2 clones. So there are many DEXs that are like Uniswap. We call those Uniswap V2 clones. And we were looking at, there are many of them on Ethereum, and there are many of them on Polygon, and there are many of them on all the other chains. And we wanted to see what was the arbitrage, not just within a chain across the different DEXs, but across all the chains. So we built this, we built a hackathon project called Western Gate. And since then, we've updated it 3 times. It's now called Odos Cat, the cross-domain arbitrage tracker. You can see it at odos.xyz. And what this project does is we're watching 8 different chains, and we're measuring approximately 35 million paths, so 35 million different arbitrage combinations. And you can see here in this example that we've measured a $10,000, this is from last week, we measured a $10,000 arbitrage opportunity across the Binance Smart Chain and Ethereum. And basically what you see here, oh, you can't see my mouse, I'm sorry. What you see here is if you would have put in USDC into BSC and swap through these different swaps, and if you would have put in Ethereum ETH onto Ethereum, this much ETH, and gone to USDC, that you would end up with more USDC than you started with. So we became really interested in arbitrage measurement and how to accurately measure or estimate the best paths. And this led us to coming up with a new algorithm. It turns out that the same algorithm you want for this is the algorithm that you want for swapping, doing optimal swaps. So we came up with a new algorithm for optimal swapping, and we built a DEX aggregator. So we look at all of the available liquidity sources on a chain, and then we try to determine what is the best route through DEXs. So each of these different colors, you can see the legend here. Each of these different colors is a different DEX. And for large trades, what you want to do when you're trying to trade online or on chain is you're going to want to split your trade up to minimize your price impact. And Odos.xyz, it does that for you. It comes up with a path for you, and it will execute your path to try to minimize your price impact on your trade. So this is our third and final talk. We have a third and final talk related to this at DevCon, and it's going to be an overview of automated market maker mechanisms. This is another field, the field of DeFi, and the math behind DeFi is another area that is going to be, it's going to be important for many years. And actually are you on semesters or quarters? This quarter you have a class. It's on Tuesdays and Thursdays, and it's related to this exact topic. So if you're interested in finance and DeFi and all this stuff, it would probably be a good class to check out. Okay, I'm near the end, and I'd like to share with you some of the hiring needs that we have. In general, we're looking for good developers. You don't have to know anything about Web3. Really, if you're passionate about software development, then we'll teach you everything you need to know about Web3. But in particular, we and everybody else in crypto is looking for Rust and Solidity developers. If you become proficient at Rust or Solidity, This is your ticket to basically any crypto company out there. They're all desperate for those skills. We're also looking for data scientists, cryptographers, reinforcement learning experts, and these are for internship positions, but we're going to be hiring from those positions 5 full-time next year. And then that's for the graph side of the house. On the Odo side, we currently have full-time needs for business development, API development, arbitrage, strategy, and capture. Currently, we only just measure arbitrage. We're not capturing any. Real-time data services and infrastructure optimization. I saw some people taking pictures, but if you would like the slides, this is a QR code to the slides. These resources have all had impact on me. And yeah, I can recommend everything here. One thing I didn't mention yet was ETH Global. ETH Global is an awesome hackathon. It happens all over the world. The next time it's going to happen is it's actually starting in Colombia in a few days, but there's going to be one in November in San Francisco. And often these crypto projects, they have lots of prize money for these hackathons. I had one of my friends, I think he made like 12K for like a weekend hackathon just himself. So if you have a team that you can collect, I highly recommend going to the San Francisco ETH Global hackathon in November. So that's all I have, and I think we have time for a few questions if we want to do that now, or we can wait till pizza.
Yeah, no, thank you, Sam. And so thank you for the talk. I've collected questions that people asked ahead of class through the question form. So I guess to begin with, Sam, I received a lot of questions around how the graph has started as a centralized service and is migrating to be a decentralized one. Mm-hmm. Could you talk a little bit about the business reasons for that, mm-hmm. The business justification for that, mm-hmm. the technology challenges, yep. and then any other challenges that come with that? And yeah. I think that may cover 20 of the questions that were submitted here. So. Okay.
Yeah. So when the graph started, a lot of this, okay, so the graph is a complex system, and adding decentralization adds more engineering difficulties. So the reason that we were centralized at the beginning was just to get something to work. But so the graph has a token related to it called the GRT, and that's what actually incentivizes all participants. And the mission of the graph is full decentralization. And that was the vision that was shared when they started the project. And basically, you can't say that you're going to start a decentralized protocol, raise money through token sales, and then just become a monopoly. It's just like, it doesn't match. Like you said you're going to do one thing, and then you don't do it. So the decentralization has been a core principle for the founders of the protocol since the beginning. So that's why we're doing it. Some of the technical challenges, well, coordination is a challenge. We have 7 core dev teams. And communication, imagine communicating and coordinating the efforts of 7 different companies, plus many individual contributors. So there's extra communications cost when you go to decentralization. Other technical challenges. Anybody want to give me technical challenges?
Well, I said that when I first started with the indexing software, and basically the economics part, the protocol part, like the whole decentralization on Ethereum, etc. part, is a layer on top, right? And so they focus first on proving that they could have a piece of software that can indeed reliably and consistently index all the data, store it on the database, serve it on GraphQL, etc. And then they eventually, built that layer on top that takes care of incentivizing indexers to run the software, to thank you, to earn money for allocating. So it's literally called allocations, to allocating their hardware to index for certain dApps. And also there's a layer that is taking care of incentivizing each query that those indexers are serving to customers. And so that's linked also to our effort with the ZK snarks, right, for the payments. But all of that is a layer on top of the software that's already running in the centralized service. So yeah, that way they proved that they can do it. They got lots of funding from various known investors like Coinbase, and they could also capture a huge amount of the market. So basically just crush everybody else and use the time to build the decentralization path, right?
Yeah, thank you. One thing that I'd like to, that I think is interesting about this, the decentralization commitment to a lot of crypto protocols, including the graph, is think about what's happening. Everything is open source, and everything is permissionless, which means that we can't shut anybody out. Nobody can shut anybody out of the graph. If everybody working on the graph today were to disappear, if anybody wanted to start it back up, they could just start the thing back up because all the code is available, all the rules are in place, and you could just start running it again. Can we say that about Web2 companies? Like, let's say some of our favorite Web2 companies were to disappear. What about all their code? That's, of course, the idea can be reinstantiated, but what about all the code they built? All right, do we have anything else?
We do. So another question that's coming up with all the different roles that are available in the graph, and in particular for indexers, it seems like the growth of indexers is pretty critical to the growth of the ecosystem. And so how is the graph incentivizing that?
Well, we currently actually have an incentivization program for bringing indexers into the network. I think we've grown from about 160 indexers to about 200 right now. And so if we see needs in the ecosystem, then we'll basically have incentive programs to try to encourage more people to come on. And in addition to that, as in the early days, it was very difficult to run indexing software. There's like a lot of DevOps skills that were needed. And as time goes on, we've automated many of the technical steps needed to run indexers.
Cool. And yeah, why don't you go ahead?
So like if I'm a DApp or like a DEX, what incentive do I have for using the graph, subgraph, versus creating my own index protocol?
Yeah. So the question was, if I'm a dApp, I want to build an application on Ethereum, why would I use the graph as opposed to writing my own indexing protocol? Well, the answer is that it's very tedious to write an indexer from scratch, and it's a time savings thing. Like if you want to write if you want to specialize in writing indexing infrastructure, which is not trivial, especially across different chains and whatnot, then that's that just takes a lot of time.
But if like it's a fairly not very well known chain, would I have to wait for the decentralized mechanism for the indexers to index it?
Yes.
How long would that process take?
That's a good question. So the question was, if it's a lesser known chain, how long might I have to wait for the graph to come in and start indexing it? And I'm wondering, I don't know, maybe you can answer this one.
So we're actually starting on an incentivized program in order to bring more chains into the graph protocol. The current chain we're working on right now is the Gnosis chain. That is due to come online at the end of this quarter, beginning of next year. For the decentralized network. On the hosted service, there's 35 chains, something like that. Most of the major chains that you've ever heard of, BSC, Ethereum, any Solana, any of those they're all available on the hosted service, and as time goes on, they will be added to the decentralized network.
I have a question. So how fast can the graph query data? So as we know that sometimes with NFT, you want to do instant sales, and these prices are very sensitive with timing. So I'm just curious.
Maybe this, how fast can the graph, how fast can we index
Yes.
the blocks that are coming in,
Yeah.
right? Is that the
So
question?
that the customer can react to that information
Yes, good
as soon
question.
as it comes up.
Alexi will answer that.
Actually, on blockchains, you can't be infinitely fast because there is a what was the term again? Basically, there's some kind of a jitter. The finality, right? You gotta wait for a certain number of blocks to be passed before you can be sure that a transaction will not revert. On Ethereum, especially after the merge, I think that was 32 blocks, 64. I mean, if someone remembers the number. So yeah, you can go fast, but you can't go infinitely fast. Because basically, what's going on? So if you think about the back when we had miners, miners were they were just doing hashes, competing, trying to find magic number that makes a block valid for the network. And basically, you can have at any time, at any point in time, multiple miners that propose a valid block with a valid magic number that starts off. So all those proposed blocks would start off from the same block, right? And you need a little bit of time, basically, for all those little branches, those uncle blocks, to be pruned off and be down to a single string of final blocks, right? So indeed, you want to be fast, but you can't go infinitely fast. So that's the thing to remember. That's a little bit weird, right, with blockchains.
So maybe if we take that into account, can we answer the question about the graph and it's the latency?
Yeah, and usually it's maybe one or two blocks. Usually it's one block-ish, 1 or 2 blocks compared to the blocks you would see, let's say, on Etherscan. But even on Etherscan, they wouldn't show you all the blocks. They would add a little delay also because they don't know for sure which one of the many proposed blocks would be the one.
Also, to add to that a little bit, it really depends on the application that you're querying. So there's, within the graph ecosystem, there's the concept of a subgraph. The graph is not just an API, it is also an SDK as well. You can go onto the graph today and build a subgraph to index a particular piece of Ethereum. Say you wanted all sales events since Genesis to today. You could do that with a subgraph. There are some subgraphs that take longer to index per block because it goes through and processes the event, does some data massaging before logging it into the database. So the answer to that question is it really depends. But again, there's a lot of factors that go into it. The slowest subgraph I've seen takes up to 5 minutes per block. That's the EIP 721 subgraph. That's your NFTs. Some of the faster ones, I've seen block times in the microsecond range. So, and that's once the block is finalized.
Thanks for the answer, guys.